In this last video of lecture 3, I want to introduce different types of films and how they are produced, the structure, the inner structures of them. Okay, so film is usually exposed in a camera, analog camera, mounted in an aircraft that is moving relatively fast. So in order to get high quality aerial images, you need to use the proper film and filter combination. You also need to choose a proper f number and also choose a proper shutter speed. Okay, obviously, the combination of film and filter is, I would say, the most important factor here. Because no matter how you adjust f number and shutter speed, if you are using the wrong film, you cannot get the information you want. Okay. So there are generally two types of films. First type, black and white films. Second type, color films. And under each category, there are, say, subcategories. So there are black and white panchromatic films. There are also black and white infrared films. So the first one is called BWP. Second one is called BWIR. The difference is that a black and white panchromatic film, it is sensitive to all visible light. Okay, it will collect information from the whole range of visible light and provide a photo. Okay, this photo eventually is black and white, but in other words, it's grayscale. It's grayscale image. It's not black or white. There is actually other scales between black and white. And another type of black and white film is called black and white infrared. This type of film is only sensitive to the reflection of infrared energy. So if for a specific pixel, for those objects within that pixel, they have very high reflectance within infrared range, that pixel will be pretty bright. If all those objects in a pixel, they have very low reflectance within infrared range, that pixel will be very dark. So the black scale level of BWP or BWIR, these levels, bright or dark, they are decided by the reflectance of pixels within panchromatic, or within panchromatic is visible light, right? Within visible range or within infrared range. I will show you examples. Similarly, we have color films. We also have color panchromatic and color infrared. So color panchromatic is simply called color image or true color image. When you are using a camera in your life on your phone or with a specific camera, when you take a picture, that picture is actually true color picture. We call it true color because all colors in that image, they are colors you can see with your eyes, right? In real world, a lawn is green, and in a panchromatic color image, the lawn is also green. So green is green. That's called true color. Green is green, red is red, blue is blue. So there are also false color images. For example, color infrared films, they can use to produce false color images, which means that red in that image is not the red you see in the real world. For example, in real world, when you're looking at a lawn, it is green because it's grass, right? But vegetation has pretty strong ability to reflect near infrared energy. And we usually use red to address the reflectance of near infrared energy. So it means that in real world, grass is green, but in a color infrared image, grass will be red. That's false color because it is not red in real world, but I don't care. I assign red to address the reflectance of near infrared energy. And vegetation has strong ability in reflecting near infrared energy. So vegetation will be pretty red in color infrared images. Okay, here comes the examples. First one, what? Black and white panchromatic. Second one, black and white infrared. Third one, color panchromatic or true color. Fourth one, what? Color infrared. Okay, so for the last two, you can say that the third one, color panchromatic, is just a true color image. You say, right? We have rows here, right? We have green vegetation, we have red vegetation because it's autumn, right? Some leaves, they are turning red. It makes sense. So like I mentioned before, here we have a color infrared image, and you can see that the whole image is actually red, right? The tone of the image is red. That's because there is a lot of vegetation within this area. It's residential. And why is it red? Why is all vegetation red? Like I mentioned, it's false color. Vegetation has strong reflectance in near infrared range, and we usually use red to address that. If it is pretty bright red, it means that the reflectance of near infrared is pretty strong. So different saturation of red is used to address the reflectance of near infrared energy. So there is a lot of vegetation within this area, so it's basically red. This image is red. Okay. Okay, let's talk about this different types of films in detail. Okay, so for black and white films, panchromatic films, they are sensitive to EMR of wavelengths between 0.3 to 0.7 micrometers. Okay, for infra, that's the range for visible light, right? Usually it's 0.4 to 0.7, but 0.3 is a little bit violet. Okay, infrared films, they are sensitive to EMR of wavelengths from 0.7 to 0.9 micrometers. That's actually the range for near infrared. And they have their own limitations. For example, panchromatic black and white films, they're limited by the almost total absorption of electromagnetic radiation shorter than 0.3 micrometers by glass. Because the lens system of a camera is made of glass. Since there is glass, panchromatic films, they cannot receive any reflectance energy that is from the light with the wavelength smaller than 0.3 because glass will absorb most of it. For infrared films, the limitation is that the photochemical instability of emulsions beyond this wavelength, which means that infrared films, they are only sensitive to near infrared band, which is I don't consider this as a very serious limitation because you want to collect information only in infrared band. So I think this is okay. Okay, here is a figure showing you the limitations of panchromatic film and B and W infrared film. Okay, so now we have two dashed lines to show you the sensitivity of film. Okay, so this dash line here, pure dash line, right? Along my cursor, right? This line here is the curve, sensitivity curve for panchromatic film. So you can say that it is sensitive actually to UV, blue, green, and red. But here we have a solid black line showing you the absorption curve of glass, this solid black line, you can see that UV light is completely not say all UV light. At the very beginning of UV light, glass does not absorb a lot of energy, but this absorption ability increases dramatically when the wavelength is closer to blue, and glass will just absorb a lot of UV light and blue light here, which means that panchromatic film cannot do a lot for blue light and UV light. Okay, so that's the limitation because most UV energy and blue energy, they are absorbed by glass, by lens of the camera. Okay, we have another dash line. It's dash point line is right here along my cursor. See this? This is a sensitivity curve for black and white infrared film. Okay, so you can say that when the wavelength is above 900 nanometer, its ability, its sensitivity drops dramatically and quickly like this. So, but like I said, it's okay as long as B and W IR film is pretty good, has pretty good sensitivity between 700 and 900. It's good enough because from 700 to 900, it's a range for near infrared, Okay, so that's black and white films. So I have some examples here for the same area. We have a huge stadium here, right, on the right side, and some buildings on the left side and a road. We have vegetation, right? We have lawn, large areas of lawn here, and also we have a parking lot. I suppose it's a parking lot, and also some trees here. So for black and white panchromatic image on the left side, it's just like an old picture you can find in your home in the basement from several decades ago. Black and white grayscale image here. Right, so the parking lot is bright because it reflects a lot of sun energy, and there are lawns here, right? They should be green, but it's black and white, so the tone is actually dark. So you can say they are in gray, not purely black. But on the right side, it's the same area, but this image is showing you the reflectance of different land cover types in near infrared range. So here, it's very interesting that you can see that this parking this parking lot is still bright because it means that this parking lot is still reflecting a lot of near infrared energy. But can you see the difference? The lawn here is very bright. It's not dark anymore. What does it mean? It means that within near infrared band, vegetation reflects a lot of energy. That's the reason why vegetation, no matter this lawn here is bright, all those trees, they are also bright. We can see some of them, they are dark because there are shadows. Right? But in general, we can say the lawn here is bright, lawn here is bright, lawn here is bright. So all those tree canopies, they are also bright. It means that, okay, vegetation is pretty good at reflecting near infrared energy. And because B and W infrared films, they are used to capture the reflectance of near infrared energy. So as a result, vegetation is bright in a BW infrared image. Okay, let's continue. Let's talk about the cross section of BW films. Okay, for a panchromatic BW film, the top layer of the film is panchromatic layer, blue, green, and red sensitive emulsion of silver highlight crystals. They are at the top of the film. And then we have the base of the film and anti-halation layer. Okay, it's pretty simple. It's 3 layers. And also here we have a cross section of BW infrared film. It still has a base layer, an anti-halation layer, but the top layer is not sensitive to visible light. It's exclusively sensitive to near infrared energy. Okay, so that's the difference. That's the difference. Okay, let's make it more complex. Now let's talk about color films. Okay, there are also panchromatic color films. They are sensitive to EMR within visible range, right? Infrared color films, similarly to infrared black and white films, they are sensitive to near infrared energy, 0.7 to 0.9 micrometers. So examples here, right? Similar not similar, exactly the same area. This is more like a modern picture, modern photo you have right now every day. So blue is blue, red is red. Everything is with the color you can see with your eyes in the real world. So color panchromatic films, they are also called true color films. So this image here, this photo here is also called true color image. Okay, here we go. Now we have color infrared image here. Like I mentioned before, all vegetation here is in red because we use red. It's not a law, it's not a rule, but it's a convention. In remote sensing area, we use red to address the reflectance of near infrared energy. That's the reason why other buildings and roads, they basically have the real color. But in order to address the distribution, spatial distribution of vegetation, we use a very distinctive color, which is red, to address that. So all vegetation here is in red, okay? So this image here is also called a false color image because red is actually not used to address red objects in the real world. Red is used to address the reflectance of near infrared energy. Of course, you can use green or blue to replace red, but like I said, it's convention. Okay. So spectral sensitivity of true color films. So unlike black and white films, the emulsion used for all color films is composed of 3 distinct layers, right? Because here there is not only gray scales, we have different actually colors. And each of these dye-forming layers consists of silver highlight crystals, which have been chemically sensitized to separate parts of the spectrum. For example, yellow forming color is sensitive to blue light. Yellow and blue. Yellow is actually the complementary color of blue, right? So yellow layer can be used to address blue light. Magenta forming layer sensitive to green light. Magenta is the complementary color of green. Similarly, cyan forming layer is sensitive to red light. Cyan is the complementary color of red. So here we have formulas, we have principles, but how to use them, okay? But before that, magenta and cyan forming layers, they are also sensitive to blue light. Okay, so sometimes we need to eliminate blue light using filters. Here, let's talk about the structure or cross-section of true color films and infrared color films. So for a true color film, the top layer is blue sensitive layer. Yellow or yellow dye forming layer. It will what? It will record the information of blue light or the reflectance of blue light from different objects within the area you are interested in. Okay, and after that, since we have recorded the information for blue light, and like I mentioned before, magenta and cyan forming layers, they're also sensitive to blue light, okay? So blue light has been recorded, but it will affect the next two layers, which are green and red sensitive layers. We don't want blue light anymore after the top layer. So we add something called yellow internal filter to block blue light. It's right here, right? It's between blue sensitive layer and green sensitive layer. So blue light sometimes can be very annoying. So after recording the information of blue light, we filter the rest blue light to make sure that the rest two layers, green sensitive layer and red sensitive layer, they are not affected by blue light. They are not affected by blue light anymore. Okay, so then these two layers, they are going to record the reflectance information within green wavelengths and red wavelengths, or green range and the red range. And then we have base layer and anti-halation layer. So this is the structure of true color films, And here is the color formation on color film or true color film, right? Blue light will firstly activate blue sensitive layer. The rest blue light will be blocked by the yellow filter layer. Then green light is going to activate green sensitive layer. Red light is going to activate what? Red sensitive layer. Near infrared or infrared will not affect the film anymore because there is no specific sensitive layer for infrared, right? And after that, when the film is exposed, when you get the film back to the dark room, you are going to process the film, right? And the processing here is a little bit different from what? From exposure, okay? So in the processing, you want to get the resulting color of blue. You do what? You do not use yellow dye layer. You use magenta dye layer to what? To get rid of green light or the information from green light, because magenta is a complementary color of green. You use cyan dye layer to eliminate the information from red light, because cyan is a complementary color of red. So eventually you have blue resulting color. So at the very beginning, reflectance of original thing is blue. Eventually you get blue on your film, on your image. So blue is blue. This is true color. And you can do the same thing, repeat the same thing for green and for red. So eventually blue is blue. What you say on this image, in this image, is blue, and in real world is also blue. Blue is blue, red is red, green is green. And since there is no layer sensitive to infrared, infrared cannot be addressed. The reflectance of infrared cannot be addressed on your true color film. So it's black. Okay. So how about infrared color film? The same dye colors are used for the same dye colors are used as for true color films, but the spectral sensitivities of the layer have been upshifted one spectral region toward the longer wavelengths. What does it mean? Yellow forming layer now is sensitive to green instead of being sensitive to blue. So from blue to green, okay, the sensitivity of yellow forming layer has been upshifted one spectral region. Why we call it upshifted instead of downshifted? Because the wavelength of green is longer than the wavelength of blue, so it's upshifted. So similarly, magenta forming layer is not sensitive to green anymore. Now it's sensitive to red. So now we have one what vacancy here. Cyan forming layer, it is not sensitive to red anymore. It is now sensitive to infrared. Okay, okay. So there is this upshifting. As a result, let's check the cross section of color infrared films. So the top layer is near infrared sensitive layer. And then we have green sensitive layer, then we have red sensitive layer, and then base, then anti-halation layer. So here comes the problem. Where is blue light? There is also blue light in the reflected energy from the ground, right? But we don't care about blue energy here anymore. And how to eliminate that? Okay, we add a yellow filter on camera, blocks blue light. This filter is not set, is not added into this IR film. We simply put a yellow filter in front of the lens of the camera to filter out blue light in advance. So there is no blue light can reach what? Can reach the film. The film is only sensitive to near infrared, right? Green and red. There is no blue light. Okay, so here we have the color formation on color infrared film. So here blue has been killed by this filter. Unfortunately, no blue light can arrive at the film. So eventually blue is actually black. Okay, okay. If there is actually a blue object on the ground, a blue bag, it will be a black bag in your color infrared image. Okay, so green in the exposure after exposure, it will what? Activate green sensitive layer. Red activates a red sensitive layer. IR activates a IR sensitive layer. But in the processing in the processing process, okay, green here will be what? Will be blocked by magenta dye layer, and the green will be portrayed as blue. This is on purpose. Okay, this is on purpose. And red will be eventually processed as green. And infrared, actually near infrared, from 700 nanometers to 900 nanometers, right? IR, near infrared energy, will be portrayed as red. If something is very red, saturated red, it means that that object reflected a lot of near infrared energy. It's very possible to be a tree or a grass, vegetation. Okay, so there is no blue objects, or we should say that blue objects in the real world, they are black objects on your or in your color infrared image. If you find a blue object in your color infrared image, in the real world, its color is green. If you find something green in your near infrared color image, it is actually red in the real world. If you find something red in your color infrared image, in real world, you cannot see the reflectance of infrared energy, but this red here is telling you that that object is reflecting a lot of near infrared energy. It sounds complex, but it's not that complex. So everything has been upshifted and blue has been eliminated. Okay, okay. In your image, blue is actually used to portray all green objects in the real world. So upshift from blue to green. Red objects in your image, they are used to green is used in your color infrared image to portray red objects in the real world. Okay, again, it's an upshift from green to red. and red is used to portray objects with a high reflectance of near infrared. Again, one up shift from red region to infrared region. Okay, it can be a little tricky, but it's very interesting. And yeah, this is the end of lecture 3, the last video of lecture 3. In the next video, I'm going to talk about the content for lecture 4, and see you there. Okay, thank you.